Hey, Algebra 2 Honor students, this is going to be Unit 5, Day 2, which I've deemed as being totally rad. So today, we're going to continue our discussion of simplifying radicals, doing some radical operations. And to get started here, we're going to talk about the connection between radical form and rational exponents. So what's a rational exponent? It's just an exponent that's a fraction. So we know a little bit about this already, don't we? We know that the square root of x is the same thing as x to the 1/2 power, and we know that the cube root of x is the same thing as x to the 1/3 power. And what we want to start building towards here is if x on the inside has an exponent attached to it already, like if this was, x squared or x to the third on the inside, what does that look like in rational exponent form? So here's an example of that. The square root of x to the 4th is the same thing as saying x to the 4th to the 1/2 power. So you can change this from radical form to that exponent form using the 1/2 exponent. And then something that we know about properties of exponents is when you do a power to a power, you multiply those together. Half of 4 is going to be 4/2, better known as 2. So I think we probably knew that the square root of x to the 4th was going to become x squared. But you can generalize that by using this rational exponent concept and eventually simplify to get x squared. It doesn't always simplify to a nice integer exponent. If you have the cube root of x to the 5th, that's the same as x to the 5th to the 1/3 power. 5 times a third is 5/3. And there's nothing much more we can do to simplify that. So just the connection between what we have in radical form and then rational exponent form. We're going to come up with a rule for this in a moment here, but what if we went backwards? So what do I mean by going backwards? What if I gave you x to the 5/3 and I wanted you to write it in that radical format? So here are two examples. If I gave you x to the 3/8 or x to the 7/4, how would I write those as roots like we had starting over here? So if you take a look at, I'm sure you can make some good connections here, right? Take a look at that rational exponent. Take a look at where those things go in root form on the left side there. If you were to change x to the 3/8, you would wind up getting that 8 becomes the root on the outside. So it's the 8th root of x to the 3rd. So the numerator goes in as the power on the inside. Similarly, for x to the 7/4, you would get that this is going to become the 4th root of x to the 7th. So it doesn't take many examples to realize what the general rule is here. And I kind of have a funny name for it. I call it the caret rule. And I like that it's called the caret rule because carets in math typically represent exponents, right? If you use the caret symbol is this one right here. That's how we get exponents on our calculators. So it's kind of nice that we have this connection to a caret here. And you might think I'm crazy, but you probably already did anyway. If you have something of the form x to the m over n power, that equals the nth root of x to the m. So where does this caret business come into play? What am I even talking about? If you were to draw something that looks like a caret around the outside of your exponent, right? You can make that into a little caret that we just picked. The bottom is the root of the caret. And notice how the denominator is the root in radical form. So what is the top representing? The top m becomes the power. Well, what's happening to the top of a caret? It's getting power from the sun in order to grow. So the sun gives the top power while that bottom root is staying fixed underground. I know, it's a little weird, but you know what? You're going to, months from now, have a question that deals with this rational exponent, and you're going to be like, man, I really wish I remembered. Oh, wait, it's the caret rule. The bottom is the root of the caret. The numerator is going to be getting the power from the sun. Okay. I mean, it's a weird analogy, but if it works, we'll go with it. So why is this kind of a good rule to have? Here are some examples that we can now pretty easily evaluate without a calculator. If I gave you, 125 to the 2/3 power, before this lesson, this have been pretty intimidating for us to do. We have no idea how to evaluate it, but now we know this is the same thing as the cube root of 125 squared. And some of you are looking at that and saying, like, Mr. All, no, I still definitely need my calculator. No, you don't, because watch what's going to happen. Don't do 125 squared in your head. I have no idea what that is. And if you know what that is, good for you. But do the cube root of 125. Make the number smaller first. So if I apply the root first, the cube root of 125, I know that that's 5, and then I have to take that result and square it. Okay, you can apply it in kind of whatever order you want, but I like to make the number smaller before raising it to that power. 5 squared is 25. And if you're like, Mr. All, I don't believe you, I don't know, check it on your calculator. 125 raised to the 2/3 power is 25. So you can check some of these that have a numerical base, like 125. If there's variables, we have to know the rules of how to convert back and forth between. So let's try something like, 81 to the 3/4 power. What would that look like? Well, that would be the 4th root of 81 cubed. I highly doubt we know what 81 to the 3rd power is. But if we're thinking about it carefully, the 4th root of 81 is a number that we know, and it happens to be 3. 3 times 3 is 9, times another pair of 3s. 9 times 9 is 81, right? Think of it that way. So 3 to the 3rd power, that's more manageable. 3 cubed is 27. Okay. Let's just do a couple more. So if I had 16 to the 5/4, what would that look like in radical form? It would be the 4th root of 16 to the 5th. 4th root of 16 is a nice value. It winds up being 2. And then 2 to the 5th power is 32. So notice how when the exponent's less than 1, it reduces the number, and that kind of makes sense. And if the exponent's larger than 1, we get a final result that's larger than what we started with in our base. Okay, lastly, really quick, if I gave you a variable base, we're not going to be able to come up with an actual value. But if I gave you something kind of crazy looking like x to the 99/16, just know that this is equal to the 16th root of x to the 99th power. Okay, and we can just quickly go back and forth between these two forms, rational exponents, and then taking a look at radical form. All right, so I know you're thinking this is pretty red so far, but let's get into some operations with radicals. So there's 2 rules we're going to talk about. Let's talk quickly about the rules for multiplying and dividing. So when you're multiplying terms with radicals, as long as the roots match. So I'm going to approach this as saying the nth root of a times the nth root of b. They could both be square roots, they could be cube roots, they could be 4th roots. As long as the roots that you're taking match, you can find that the product is the nth root of a times b altogether. Which kind of makes sense to us, right? Because when we simplify radicals, we break it down actually in the reverse way. We break it down into 2 different terms that are being multiplied. So hopefully that rule is not so crazy for us. So then the rule for division, similarly, if the roots match, the nth root of a divided by the nth root of b. Altogether, you can kind of squeeze that into one big nth root. It would be the same thing as the nth root of a divided by b. Okay. So thinking about some little quick practice questions with this. If I gave you -2 times the square root of 5xy to the 4th times -4 square root of 15xy. Okay. Because when I multiply these, we're both taking the square root in these cases. We're allowed to multiply them together with the quantities underneath. So what happens with the coefficients out in front of those radicals is that those will just get multiplied as well. -2 times -4 is 8. And then it becomes the square root of 5 times 15, which is 75. X times x is x squared. Y to the 4th times y is y to the 5th. So when you multiply, I mean, it's great that we know the rule, but now we have to think about, can we simplify this and express in simplest radical form? That's really the whole goal of this unit. Once you perform an operation, can we simplify that any further? So we want to break this apart into 2 radicals, one that's all the perfect square pieces, and then one that's all the non-perfect pieces. So the biggest perfect square that goes into 75, Hopefully you're thinking about 25. That goes in 3 times. Let's see, for x squared, actually that whole thing is a perfect square, so that can go in the first perfect square radical. And for y to the 5th, we have to break that apart because the largest amount of y's that I can take that are a perfect square, the largest quantity that's still divisible by 2 is y to the 4th. You can take most of them, but that does leave 1 y left over here. So from there, take the square root of that perfect square. That would be 5xy squared times your radical 3y. All right, take the square root of each of these terms individually. Remember, that means take the exponents, divide them by 2. And then the final step is just multiplying the coefficients, the 8 times the 5. So it's 40xy squared times the square root of 3y. That is the final answer for something like number 1. All right, number 2, let's do one where we have to divide the square root of 72x to the 4th, y to the 7th, divided by the square root of 3xy squared. Okay. Because these are both square roots, we can use the rule up above that if you have the nth root of a over b, it's the nth root of the quotient of the top divided by the bottom. Okay, so this is going to get sucked into one big radical here, and you can just divide the terms accordingly. 72 divided by 3 is 24. X to the 4th divided by x. When you divide, you subtract those exponents, so now we have x cubed. And then y to the 7th over y squared is y to the 5th. Okay, so from there, we want to think about, can I simplify this? And the answer is, of course we can. Break this apart into the perfect square radical, the non-perfect radical. Let's see, 24, that's, I think the biggest perfect square that goes in is 4, and it goes in 6 times. From x cubed to the largest perfect square we can take from it is x squared, which leaves you with 1x over here. And from y to the 5th, we can take out y to the 4th and leave 1y left over there. So this is a perfect square now. Take the square root to get 2xy squared times the square root of 6xy is your final answer. Much more to come with radical operations. We can do the same things with cube roots and fourth roots, so we want to kind of really pay attention to what is the root that we're taking. We'll do some more practice with that later on. All right, let's talk about a process called rationalizing denominators. This is something that you should learn in geometry. I'm not quite sure. Every teacher teaches it, so you'll have to tell me next time I see you if it looks familiar. But here's what I mean by rationalizing denominators. If you have 3 divided by the square root of 6, in simplest radical form, we don't leave radicals in the denominator. And the best explanation I can give you as to why is because you're dividing by something that's a decimal that never ends and never repeats. So it's not really a proper form to leave fractions in with radicals downstairs. So the way we're going to rationalize the denominator here is actually by multiplying the top and bottom by radical 6. Multiply by that radical quantity on the top and bottom. We're allowed to do this because we're just really multiplying by 1. Something over itself is 1. So in the top, we get 3 radical 6. And then radical 6 times radical 6 on the bottom is, hopefully you're just thinking it's 6, right? Because if you multiply those, you get the square root of 36 left over, but the square root of 36 is 6. So when you multiply 2 radicals that have the same quantity underneath, we just get that same number underneath the radical there. Oh, and hey, 3 goes into 6 twice. So the final answer here would be radical 6 over 2. And this is in simplest form now that we no longer have a radical in the denominator. So maybe just another quick example like that, 8 divided by radical 2. Since we can't have radicals in the denominator, in this case, you multiply the top and bottom by radical 2 to get 8 radical 2 over 2. Did that kind of fast, right? But radical 2 times radical 2 is radical 4. Oops, that's just 2. Oh, and hey, 2 goes into 8 4 times. Okay, so it's technically, I guess, 4 radical 2 over 1, but anything divided by 1 is itself. So in this case, we wind up getting 4 radical 2. is the simplest form of 8 divided by radical 2. Okay, so a lot of times if you're doing multiple choice questions, when it says express in simplest radical form, if the denominator needs to be rationalized, because currently it's irrational, then that's a step that we'll wind up taking. All right, so then the last thing we have to do with rationalizing denominators is something like, what if you had a binomial in the bottom, 2 plus radical 3? Is multiplying by radical 3 on the top and bottom going to cancel the fact that we have radicals downstairs? And the answer to that is no. If you multiply the bottom by radical 3, you'd have to distribute it over here, and then you still have a radical 3 attached to the 2 now. So what we're going to wind up doing for examples where there's binomials is we are going to multiply the top and bottom by the conjugate. So I'll kind of explain what the conjugate is. If you have the expression two plus radical 3, that's my current denominator. The conjugate is very simply the same terms with a minus sign in between. So the conjugate is just changing that middle sign. So if I had 5 minus radical 7 as my expression, I would multiply by its conjugate, 5 plus radical 7, to eliminate the radicals in the denominator. If I had negative 3 plus radical 21, the conjugate is negative 3 minus radical 21. So notice how the first sign doesn't ever change. It's just the sign in the middle. So be careful about that. It's common for students to want to just say, oh yeah, I'll negate both, because we do that sometimes in math. But the conjugate is just changing the middle sign only. Keep the first sign the same. So let's go back to that example, 5 over 2 plus radical 3. So what I'm going to do is I'm going to multiply the top and bottom by 2 minus radical 3. So let's talk about what happens in the numerator when I do that. Distribute the 5 to get 10 minus 5 radical 3. When you multiply conjugates, something really special happens all the time. Let me show you what happens down here. If you do FOIL, which is first, outside, inside, last, okay? 2 times 2 is 4. If you're a box method, you'll get the same thing, by the way. 2 times negative radical 3 is minus 2 radical 3. The inside, 2 times radical 3 is plus 2 radical 3. And at the end, you're going to get minus radical 3 times radical 3, which is just 3. When you multiply conjugates, you'll find that the middle terms always cancel. So the denominator is just 4 minus 3, which I guess I really could have simply wrote as 1. Okay, so if you're unsure about what to do, of course multiply it out, but you'll find that you get this pattern to emerge where the middle terms always cancel. And by the way, when you divide by 1, we don't have to write that anymore. Something divided by 1 is itself. So the final simplified form of this initially, 5 over 2 plus radical 3, is 10 minus 5 radical 3. Okay, let's try another one for practice just to make sure we kind of got the idea of what's going on here. So if I have 5 plus radical 6 up top. Now I don't really care about the numerator's radicals, but when we have radicals in the denominator like this, we're going to have to multiply the top and bottom by the conjugate of the denominator to get there to be no more radicals in the denominator. So what is the conjugate of the denominator? In this case, it's going to be negative 3 plus 2 radical 6. Remember, keep the first sign the same, just change the middle sign from this expression. All right, so what is that going to leave us with? Well, in the numerator, 5 times negative 3 is negative 15. I'm going to actually write my work down here. 5 times 2 radical 6 is plus 10 radical 6. The inside is minus 3 radical 6. I'm just doing FOIL right now. And then radical 6 times 2 radical 6 is going to be plus 2 times 6, which I realize is 12. But I'm running it that way because the 2 is just going to get multiplied by this pair multiplied out, We know radical 6 times radical 6 is 6. So eventually I'll write that as a 12. Okay. So in the bottom, we should find that when I do this, the inside terms cancel. So negative 3 times negative 3 is 9. Negative 3 times 2 is negative 6 radical 6. Negative 2 times this negative 3 is plus 6 radical 6. And there we go. Those are going to cancel. Okay, just be careful with the last terms. Negative 2 times 2 is negative 4 times radical 6 is 6. So I realize that last number becomes minus 24. But if we write it this way at first, maybe that makes sense that the product of 2 radical 6 and 2 radical 6 is really 4 times 6. All right, we can clean things up on the top, right? Because on the top we have negative 15. These combine right here. They're like terms. 10 minus 3 is now 7 radical 6s plus 12. The bottom is going to become 9 minus 24. And then lastly, if you combine like terms, the negative 15 and the 12 up in the numerator would combine to give you negative 3. So negative 3 plus 7 radical 6. Oh, and then 9 minus 24 in the bottom, that would be negative 15. And I'll let us stop there, right? I mean, the bottom's definitely a rational number now, so we have officially rationalized the denominator. And is there room for error with this process as far as multiplying all these radicals? Of course. But if we're careful about the process, by tomorrow when we do the recap, I might even shortcut this process a little bit by not writing those inside terms. Because like I mentioned, when you multiply conjugates, those will always cancel out no matter what. And that will be a common theme in what we do later on in the year when we keep talking about conjugates. So we'll do some more practice with this. Next time I see you, let me know if you have any questions. And of course, have a fantastic day.